Good afternoon. My name is Pavel Abdulkin. I'm the head of chemistry for Dolomite and the entire Black Trace group. And today I'll be talking to you about fabrication of PLGA nanoparticles using continuous flow systems provided by Dolomite. So what we thought we'd do today is we'll show you a short presentation describing the principles of making nanoparticles. We'll explain what consumables we're using. We'll give you a quick overview of the system, and then I'll take some questions. So without further ado, if we go to the slides now. So learn how to make PLGA nanoparticles in flow. So first of all, a little introduction to the team I represent, which is the particle engineering team. We're a team of chemists and engineers working together to create nanoparticles and microparticles in continuous flow. We focus on biomedical and pharmaceutical industries, and we supply standard products to our customers, such as emulsion stabilizers and nanoparticles. But other than that, there are two ways that customers interact with us, and that is by seeking advice on the systems that they'd like to purchase. And finally, we undertake proof of principle studies for our customers, which enable them to take system purchase forward. A little bit about Droplet Microfluidic technology. Any continuous flow system is as good as the pump. Unlike other suppliers of microfluidic equipment, Dolomite uses pressure pumps. And within a pressure pump, you have a reservoir into which a liquid sample goes, and that sample is pushed through the system using pressure on top of it. And as you can see on the slide, it goes through a flow sensor, and the software that we use has the capability of chasing a specific flow rate set to within 1 millibar pressure of the pump. You then flow in through droplet microfluidic channels into a chip, which you image directly, and based on that, you can create your droplets, nanoparticles, etc. So how does it work? Well, fundamentally, you have a chip, which is precisely manufactured using lithographic techniques, and you have two immiscible liquids, or miscible liquids in the case of nanoparticle fabrication, which are combined at the junction. In the case of immiscible liquids, the droplets will be pinched off. In the case of miscible liquids, precision mixing is achieved. The system only puts pressure on the back of the liquids, so there's no active agitation involved. And so we say that in droplet microfluidics, particles are made with love, whereas in batch, they're made with hate. The systems are very flexible, and there are a number of chip architectures that we use. So here are the 6 common ones. So users can create segmented flow, and that is typically used for chemical reactions when you want to separate individual batches of chemistry, and you also want to make sure that chemicals within the droplet or slug do not contact the walls of the reactor. This is very common in nanoparticle formation, because nanoparticles are very reactive and like to absorb to the walls of the reactor. In other cases, you simply make droplets. This is very common for us when we make microparticles. In more complex cases, you make in double emulsions when you have either an oil droplet on the inside of the water droplet suspended in oil, or the other way around, water and oil in water, commonly known as WOW emulsions. Another mechanism is for encapsulation. So we have a sister brand called Dolomite Bio, and all they do is encapsulate cells in droplets for single cell research applications. The mechanism we'll be working with today is the 5th mechanism alone shown, and this is growth of nanoparticles fundamentally within droplets, or in this case in sheaf flow. And this is a way of controlling nanoparticle growth precisely by limiting supply of stock material going into the nanoparticles, so limiting their size this way, but also by separating nanoparticle reservoirs where nanoparticles are created from the rest of the system, so that they don't touch the walls of the reactor, thus blocking it. And then finally, you can create Janus particles using our 2 reagent systems, where 2 immiscible liquids are combined at the junction. So there are a number of microfluidic junctions that we fabricate, and they enable a wide range of emulsions or particles. So on top, you can see junctions ranging from 5 microns to 50 microns to then 300 microns. Bigger or smaller ones are available at request, but these are standard materials. So this is our 5-micron droplet microfluidic chip, 2-reagent 50-micron chip, and a micromixer chip. Now, you can use all of these for creation of particles. So here are some examples. So you've got microparticles down the bottom, and you can image them quite easily. These are about 75 microns, and these are agarose beads we make. Next in line is a double emulsion, where you've got a water droplet on the inside of PLGA droplet in dichloromethane, all suspended in water. And then further along, the same system, but now showing a multiple emulsion system, where you've got multiple water droplets on the inside of the PLGA droplet. And all of these have applications in drug delivery and controlled drug release. Now, the systems come in two flavors or two throughputs. So there's an R&D system, like we will be demonstrating after this presentation, and that's based on a single junction. So in that single junction, you'll typically have a T-piece where two liquids meet at the interface, thus creating droplets or particles. You typically have 3 pressure pumps, and you typically have a microscope to image the chip. And these systems are capable of a gram throughput per day, so typically anywhere between 1 and 10 grams a day. Now, if you want to scale up, you could go to a Telos system, and Telos system scales up microfluidics in 3 distinct ways. First of all, it increases flow rates of both continuous and droplet phases by managing flow very well on the chip, and by managing flow resistance. It increases the number of junctions working together in parallel, and increases the number of chips working together. So typically, a Telos system would increase the throughput by about 2x. It will increase the number of junctions by 7x on one chip, and you can have a total of 10 chips on a single Telos slice. So typically, you achieve over 100x increase in throughput by going from a single junction system to a Telos system. And if you're looking at the world of emulsions, Telos is capable of producing about 40 liters of emulsions within a 24-hour period. With nanoparticles, with nanoparticle formation like we have here, that is substantially increased to about 50 or 60 liters a day. So let's look at ways of making PLGA nanoparticles. So first of all, let me illustrate why continuous flow is a much better technique for making nanoparticles using this example of gold, and this is something we've done at the very early stages. So when you're doing nanoparticle synthesis in batch, or any other synthesis for that matter, the same set of problems persist. So you're adding one liquid into another, and mixing is slow, typically of an order of seconds. You've got temperature gradients that are set up across a batch vessel, and you've got concentration gradients, which are set up across a batch vessel. Now, that means that every single nanoparticle experiences a different set of conditions during its growth. So you have a range of reaction conditions, and that leads to a range of particles, like you can see in the TEM image on the right. Now, this is completely different when you go to a flow system. In a flow system, channels are on the micron scale, and so mixing is very, very fast, of an order of nanoseconds or microsecond mixing time. You can set up separate zones for nucleation and growth, where you can control conditions separately. And most importantly, each single particle goes through the exact same path, i.e. all of the growth histories are identical. And if all of the growth histories are identical, then all of the particles will be the same. So you can see the TM image on the right is the same gold nanoparticle system now synthesized in flow, and the monodispersity is substantially better. So how does that translate to making polymer particles in flow? Well, the same Mia theory persists and guides the synthesis of these particles. So what we're doing is we are taking PLGA solution in a water miscible solvent. So typically this is PLGA dissolved in acetone. And what we're doing is we're taking it to a junction where we're mixing it with an anti-solvent, in this case, water. And what this does is at the point of contact between water and acetone, mixing occurs, and solubility of PLGA decreases substantially. So PLGA starts to nucleate and crush out of solution. So what you're setting up is the fast growth zone where PLGA strands nucleate into particles and more strands are being added to them. And then throughout the rest of the chip, the system continues to grow up until a state of thermodynamic equilibrium, but it continues to do so at a much slower pace. Now, Making PLGA particles on its own isn't particularly interesting. What's interesting is adding APIs to them. And the big advantage of this system is the use of acetone and aqueous phases is very similar. So you don't have a huge excess of aqueous phase. In fact, you normally run at 5:1 flow ratio of acetone to water. And what that means is you can bring your API in using an aqueous line in case your API is hydrophilic, or you can bring your API via the droplet line in case your API is hydrophobic. So it's a very flexible system. So let me show you two methodologies that we commonly use for PLGA nanoparticle synthesis. Each has its benefits and drawbacks, and we can talk about each one individually. So system number one is based on what we call a 5-input chip. And what's happening here is the PLGA solution will be brought in through the central channel, marked in yellow, and the anti-solvent solution will be brought in only two channels immediate outward from it. And you'll also have what we call flushing fluid. What is the purpose of the flushing fluid? Well, the biggest problem with making PLGA particles in flow, or any nanoparticle in flow, is that nanoparticles will tend to adhere to walls of the channel and thus block it. And with any other system, that's a problem. So what this chip achieves is it creates a protective flow of material on the sides of the channel, and then creates a solvent anti-solvent system within the channel where nanoparticles can nucleate and grow without restriction and be safely taken off the chip. So this system currently works and has currently been tested for PLGA concentrations anywhere between 0.5% to 2% this system has been verified with our own emulsion stabilizer called Aquaphase, and the flushing fluid is typically deionized water. So the big benefit is, other than water and a little bit of an emulsion stabilizer in there, the only other material in the solution is PLGA nanoparticles. So it's a very clean, very flexible system. So if we look at the results that we typically achieve, so if you look at the image on top, then you can see the nanoparticles coming off from the jet that's being created. And what we find is we can operate this system for 5 hours without any human intervention. We are flowing the droplet phase, so this is acetone PLGA solution at a flow rate of about 20 microliters a minute. And we can easily manipulate the system to create particles between 100 and 200 nanometers. And this is done by adjusting relative flow rates of the PLGA solution and the Aquaphase solution. Now, let's look at the second method. And the second method is really designed to increase the range of particle sizes available, and it is designed to increase throughput. So here we have a 3-input chip, and this is one of our 100 micron 3D pore chips. Now, this chip has a hydrophobic coating. This has also been verified for 0.5 to 2.8% polymer solutions. This has been verified with Aquaphase, our own emulsion stabilizer, and this has been verified with Fluorophase. So what is Fluorophase doing there? Well, Fluorophase is performing the same function as the flushing solution did in the previous method. So this is a hydrophobic chip. Fluorophase is based on fluorocarbon oil. So what happens is when you flow Aquaphase and Fluorophase down this chip, the first thing that happens is you'll make droplets, aqueous droplets inside fluorocarbon oil, and the fluorocarbon oil will be on the outside, obviously protecting the aqueous droplets from adhering to the sides of the channel. And the moment you start flowing the acetone solution, the fluorophase is designed to break, so you will not be stabilizing droplets anymore. You'll be stabilizing a jet, and fluorophase will adhere to the walls of the channel, creating a 1 to 5 micron sheaf flow on each side, thus protecting nucleation, thus protecting the channel from nucleation of polymer particles. So fluorophase is based on silicon nanoparticles. Fluorophase is suspended in fluorocarbon oil, and so when you collect your particles on the output, fluorophase is so heavy that it'll precipitate to the bottom within minutes, and all you have to do is simply collect the surface fraction from your collection vessel, separate it, and collect and undertake your post-processing. Equally well, you can bring in API through the aqueous line, and you can bring, in the case of hydrophilic API, and you can bring hydrophobic APIs through the polymer line in the acetone solution. Now, what happens if we look at the results? Remember, I mentioned that in continuous flow, typically, when you undertake micromixing, you will have adhesion of particles to the walls. And in the first slide on the right, you can see typical results from DLS obtained this way. So this is you do get 100 nanometer particles in our micromixer chips, but you also get a long tail of particles in the 300, 400, 500, 600 region. And that creates this broad size distribution. So this is good enough for a lot of the applications, but being Dolomite, we are perfectionists and we want to tighten those size distributions up until they're absolutely perfect. So that methodology really enables us to tighten the size distribution of the distribution of particles available. Another thing it does is because we've got precise control over the flow rate of aqueous solution, and we've got precise control over the flow rate of the polymer solution, we can increase the size range of the particles available. So we can precisely generate 500 nanometer particles, we can precisely generate 400 nanometer particles, or in this case, we're showing 50 nanometer particles and all the way up to 800 nanometer particles. It's a very flexible system for a range of particle sizes that you'd like to generate. You're also increasing the flow rate of droplet phase by 2.5 times. So this is 50 microliters a minute now. And we've been operating these systems for 5 hours continuously with no human intervention. These systems can run in low pressure, so 200, 300 millibar on the set to pressure pumps, or the system, the way we actually recommend to drive these systems is in high pressure mode, so 2, 3 bar. The reason for this is if you get a little bit of collection of the polymer on the sides of the channel, despite the protection, the high pressure tends to shift that through straight away, and you never get any problems with clogging. So just to reiterate, let's have a look at some of the results that we obtain. So we've got two systems capable of throughput of up to 50 microliters of solution a minute. They can generate polymer particles from solution of 0.5 to 2 weight%, and these systems can run for 5 hours on end and generate non-dispersed size distributions. And this is substantially better than anything available using conventional micromix and flow, and miles better than anything available in batch. Now let me spend a few minutes talking about the reagents that we have shown you there. So we find that a big problem with supplying customers with systems on their own is that customers tend to play around with different chemicals and achieve different results. So in order to prevent that from happening and actually substantially increase the throughputs of these systems, we've introduced two emulsion stabilizers available through Dolomite website now. The first one is a polymer solution designed for work with PLGA nanoparticles and microparticles. And this is an aqueous solution of a range of polymers and stabilizers and viscosifiers as well. And this is called Aquaphase, and this is available through the Dolomite website now. Another one is the fluorophase. This is silicon nanoparticles and fluorocarbon oil, and they are designed to make Pickering emulsions. They're designed to prevent leakage from droplets, and they're fantastic at making water droplets in fluorocarbon oil. Both of these are available now. So please have a look at the Dolomite website and have a look at those two emulsion stabilizers. We find that users report substantially improved throughputs, substantially better manipulation of emulsion stabilizer in terms of the ability to remove the emulsion stabilizer from the finely formed particles and the ability to merge droplets if needed to. And also both of these are biocompatible and washable. They're inexpensive but highly effective. So in conclusion, as we said, we've got two systems for stable nanoparticle formation. Both are based on 3P pumps and two different chips. You can achieve throughputs of up to 50 microliters a minute. Both of these systems are scalable using Telos system. So the throughputs can be increased by 100-fold, and you can be generating nanoparticles between 50 and 800 nanometers. And if you talk to us, we'll be happy to assist you with choosing your system. So thank you for your attention. And if we go to the camera view now, I'll give you a quick overview of our system. So as we said before, we've got 3 pressure pumps in line, and each of the pressure pumps contains a pressure reservoir in which we've got our solutions. So Aquaphase, PLGA solution, and fluorophase. Each pressure pump is equipped with a flow sensor mounted using a flow sensor interface. That flow sensor is a heat trace flow sensor, so it will it doesn't interfere with the flow, but it measures flow rate down to 0.1 of a microliter a minute. So that generates very precise flow through the system. And the system has the capability to operate in pressure control mode or in flow control mode, where we set a flow and the system will automatically adjust pressures to match that flow. So once we've dealt with pumping, the chip is connected using standard HPLC tubing, using a standard H interface. The chip is observed directly using a microscope, which observes it by flashing an LED array down the chip and reflected back through the mirror. And then we're simply collecting into a simple laboratory reservoir. But in more complicated systems, that can be done into designated glassware, can be done into a large batch vessel. The chip is mounted using Dolomite interfaces. So these are very easy to do and undo, like that. And then a chip would mount in easily and securely. And this interface is good for up to 20 bar, and so can generate substantial throughputs. So that's the system overview done. And these are the motion stabilizers that I've talked about: Aquaphase, Fluorophase, and Fluorostop, which is the which is a counterpart to Fluorophase. It's a component designed to break emulsions precisely for when you want to release and remove the surfactant from your final beads. So with that said, I'd like to take some questions from you guys now. So let's move to the Q&A session.